Vai.
Ok, allora, come al solito, cominciamo con l'outline. And maybe I should switch to English, right? Okay. So, I changed this interface. So here we are, and we are. Okay. The lecture of today starts from a very, maybe you know what, I can switch off the webcam because I'm looking somewhere else. So it's based, the lecture of today is based on a observation, on a remark that I will make right now in the beginning. And starting from this remark, we will start the lecture. That will be a classical lecture with a single file containing slides, a single PDF file with slides, different from the other lecture from the last 2 days. So the observation, the remark is, I would say, a trivial remark, but very, very important, is the fact that sometimes what we want to learn has certain properties. Those properties, certain properties, I mean, that we know in advance. I mean, properties, a priori knowledge for the function f star that we would like to know, okay? Continuing the notation from the other day. So we want to know this function, and up to now we said we don't know anything about this function except some data, some training data, some test data. Now I'm saying that usually, not usually, but quite often, it happens that we know something more about this function. That is not additional values, additional points, additional items for training and test, but sorry, but certain properties. For instance, I made here a few examples. In medical imaging, some expert, some surgeon expert could tell us that certain textures, certain shapes in this medical image is characteristic of a certain type of cancer. Or in a game, we certainly knows illegal moves. Okay, so we in advance knows that if the function is predicting in a certain position a move which is illegal, that is stupid because that move is illegal. Okay, or going back to the regression learning problem, we are going to learn a function. We could know in advance that the function we are going to learn is, I don't know, is a price. So should be positive. So the function to be learned usually has bounds that we know in advance. So it would be sort of stupid trying to learn any function with unbounded function. And or another example, you could know that certain training samples are more relevant, more important than others. Okay, and you can always, and I would say, if you have such a knowledge, you should always use this kind of knowledge to make learning a little bit easier. For instance, in the case of medical imaging, if you know that certain shapes have certain meaning for the problem you are learning, you could input to the machine not only the image, but also whether such a shape is present or not. You could add a dimension where you put 0 or 1. 0 means that feature is not present. 1 means that feature is present. Okay, this would be called feature augmentation, feature engineering. Or, as we do in programs that play games, you could filter illegal moves, meaning that if the model is predicting an illegal move, then you filter that out and you make a new prediction. Or or better said, you assign, you mask the probabilities of the illegal moves with 0. This is how it is usually done. Or if the function you want to learn is bounded, you can impose those bounds on the model. And we already did that yesterday, very quick, actually. I showed you a slide. In the classification problem, the last layer should predict a probability distribution. Predicting a probability distribution means that you are predicting several numbers which are between 0 and 1 and which are summing to 1, okay? Such a non-trivial bounding is made, making the last layer output as a softmax function. Or if you have training samples with different with different importance, you can just weight them more or less in the loss. Remember, the loss was a sum over the training samples of the let's say x f hat of xi minus yi squared. Okay, this was the loss was compounded by such a sum. If you think that x1 is more important than x2, you could put to this term in the loss x1, you could put a number here. Okay. You could put here a number 2 if you want to count this in the sum twice, doubling its importance. Okay. Of course, questions if you have some. We say that we are injecting domain knowledge in the problem, okay? Our learning problem is made easier by our domain knowledge. And it is sort of natural. If we know more, then what we are doing should be easier, okay? Now, I want to focus on a single very common property that happens. That will be the property driving the today lecture. This property is that the function we want to learn is invariant or equivariant under the action of a certain group. Now, you already know an example of this, and this is the example that will drive our lecture. So try to remember and tell me. I told you this property for a task we have analyzed yesterday. So this is the point where I stop and I ask you to tell me if you have in mind a very classical, very natural task made by artificial intelligence today that is invariant or equivariant under some action.
Image recognition.
Image recognition, yes. And which is the group under which image recognition is invariant or equivariant? Translations. Perfect. Image recognition is, let's say, if we say image recognition, this is invariant by translations. Okay, I said something like this yesterday, but this is very, very natural. I can repeat just without drawing any horrible image that I will draw. And it is the fact that if I'm recognizing whether in any image there is a cut or there is not a cut, and if I move this cut from the top left corner to the bottom right corner, I translate this cut in any other point, position in the image. I can also rotate the cut, actually. If I do this kind of transformations, then if the picture was containing a cat, then it should still contain a cat, right? There is any reason for a model to be able to give different answers on these two pictures? Because in terms of orbit space, since we are mathematicians, we can talk with this kind of language. In terms of orbit space, these two images are exactly the same point. And so the function should have the same value on these 2 points. Okay. This remark is the starting observation of the topic of today, which is geometric deep learning. So geometric deep learning is just applying this observation to deep learning. Okay, so now we have this file, which are slides, and these files are taken from a geometry of deep learning PhD course, and this is the link. If you want to see it, there is the lecture I gave at university for the University of Bologna course last year, or a few months ago, actually. Okay, so let's start with these slides. Now, the main acknowledgement. This is a very important acknowledgement. These slides and topics are all of them extracted from a beautiful online course, which is Geometric Deep Learning, which was taught in a master in artificial intelligence last year by these names: Michael Bronstein, Joan Bruna, Cohen, and Petar Veličković. These names are the 4 people that has founded this topic that is known today as geometric deep learning. So I would say, if you want to study this kind of topic, besides listening to me now, you should for sure look at this course. This course is a playlist comprising several lectures, hours of lectures, and the slides that I'm presenting to you are more or less extracted from all those several hours of lectures. Okay, so it is, of course, very condensed. A lot of things are missing, but I tried hard to extract exactly the most important ideas from here. Okay, so let's start with this picture. Now, today, we know, we are mathematicians, we all know that geometry means properties up to certain symmetries. Okay, if I ask you to define what does it mean geometry, this would probably be the sentence, the definition that would come up to the mind. But at the beginning of the last century, it was not this way. There were several there were several different geometries. There were affine, Euclidean, hyperbolic, and so on. Several different geometries shown here as a zoo, shown here as different animals. And mathematicians were all wondering which one was the best geometry. I mean, they are different kind of things. There should be one which is the best in some sense, or the right one. Or at least if there were some hierarchy between geometries, one which is more powerful than the other. And then Felix Klein came and he said, okay, listen, actually, it is not a matter of which geometry is best, is better than the other. We are just looking at different concepts. Certain concepts exist only with respect to certain symmetries. symmetries are the heart of geometry. This is what defines a geometry. And in this sense, this is what characterize and distinguish and make a hierarchy, if we want, between all the shown geometries. This one. Because, for instance, the Euclidean geometry is considering the notion of angle, distance, area, parallelism, intersection. So any symmetry with respect preserving this property is relevant for Euclidean geometry. But if we have two shapes which are the same with respect to parallelism and with respect to intersection, but as different distances notion, different angles or different areas, well, those shapes would be different for Euclidean geometry, but would be the same for affine geometry. Okay, this is, I mean, this should be trivial as an idea now for, in particular for us, we are all mathematicians, but it was not this way 130 years ago. Okay, so Felix Klein is the guy who started it all. We should thank you very much because the geometry we studied today is due to him. And in particular, we should remember, starting from now, for this lecture, I mean, that symmetries are vital in geometry. And the main idea of geometric deep learning is that what happened yesterday in geometry is now happening in deep learning. In what sense? Well, up to this moment, if you start studying deep learning, you will discover that there are several different architectures in deep learning that work very well for a certain problem. As Tommaso pointed out, I seem to remember in the first lecture, one of the feeling you should get when you are using this technique to solve a problem, the first question you should pose yourself is, which kind of architecture, which kind of model should I use? And this is true. There are problems, there are architectures that work very well for certain problems. We have seen convolutional neural networks work very well for images. Graph neural network, you can image, works very well for problems where the input is a graph. Transformers, whatever they are, not the big robots in the movies. Transformers are a family of very famous models, very effective models. They work very well for time series now. And people are starting to ask, okay, which one is the best? So for instance, when Transformers came out, everybody was going to use transformers also for images, despite the fact that convolutional neural networks are very effective for images. Because one is tempted to say, okay, since transformers work so well for a certain problem, maybe this is the ultimate model that is working very well for everything. So I will try to make it work on images, make it work on other things, and so on. And by the way, transformers works very well also on images, but this is not the point. So we are in a similar situation where we should try to understand those models maybe from another point of view. And geometric deep learning is trying to do exactly the same as in geometry. It's trying to unify apparently different deep learning architectures. And as I was saying in previous slide, all these different geometries, they follow in some sense a similar blueprint. They are all geometries or properties invariant for the action, for a certain action of certain groups. What changes are the symmetries. Okay, but the blueprint, the main idea, the foundation of what are these Euclidean affine and projective geometry is the same. Okay. Yesterday I was talking about the universal approximation theorems, and now you know that you can approximate any function with a neural network with one hidden layer. Okay. And so, I mean, we are mathematicians. I think the first thing that come out to our mind is, okay, but come on, we don't need any fancy model. We can approximate every function with just a 2-3 layers neural network. Okay, so why should I use very complicated models? Okay, but is this observation really useful? Can it really solve any machine learning problem with the same model, with the same, let's say, by analogy, general geometry, meaning in this case a 2 layers, a 3 layers neural network? Or should I use a more specific architecture for any different model, for any different, problem? Now, the fast answer is no, I can't use this universal approximation property. I can't use a simple 2 layers neural network. And to justify this, I want to show you, maybe there is an image here. So look at this question. We are saying that with a 2 layers neural network, something very simple, I can approximate any function in a certain family, let's say any continuous function. But now the question should be, okay, how many samples, how many training items are needed to be sure that the approximation I have found, the F star, the F hat I have found, is approximating my unknown F star up to accuracy epsilon? How can I be sure? How many samples should I have in order to say that? Well, there is a theory. This question has an answer, and the answer is the following. If we want approximation to accuracy epsilon, we need at least, if we want theoretical guarantees that we are going to have this kind of approximation, we need at least epsilon to the power of d samples. Remember what is d? D was the, okay, no, yesterday D was another thing. D in this setting is the dimension of data. For instance, if we want to classify 32 by 32 images, then D is equal to 32 to the power of 2, which is more or less 1000. Okay, and this means that if we want approximation with epsilon, let's say 1/10, which is a very bad approximation, by the way, we would need 1/10 to the power of 1000 samples. And this is very well pictured by this. There are not enough cats and dogs in the world to make such an estimate. Okay, so this is something which is usually known as an instance of Bellman curse of dimensionality. In machine learning, you will often find this term, meaning that the dimension, the things you need are growing exponentially with respect to something that is usually which is usually big enough to make this exponential growing, making your problem ineffective and unusable. Okay. How are we going up to now? Okay, so this is not really related to the two-dimensional layer, to the two layers neural network. This is theoretical thing. So it's always true, but of course not if we assume we know something more on the problem. Okay, so let's go. Here. Okay, what can we do to break the curse of dimensionality? We can do something that here is stated as a theorem. For a mathematician, it is a trivial theorem. It is stating that if the neural network output is invariant to a group, then its output can be expressed as functions on the orbits of the group, meaning that if f from x to, let's say, r is invariant under the action of a certain group G, then f actually factorizes, if you want to use this term, on the orbit space in this way. Factorizes, meaning that f is actually the composition of some f tilde and the projection pi of x over G. Okay, meaning that f is known as soon as you know f tilde. Okay, so this is a theorem in 1969. Okay, is a from the point of view from this kind of terminology and notation, almost the definition of the orbit space, but it is very important in machine learning because in this case, how can we break the curse of dimensionality? Well, now the space x over G has a smaller dimension, right? As soon as G is not discrete, this space has a smaller dimension. So that exponent D is now smaller in the course of dimensionality. So this is clearly clearly helping in reducing this course. It will not be enough anyway. Okay, let me see what is here. Okay, this is again some brief introduction to learning. Maybe we don't need it anymore. We already told a lot of this, but just very, very quick, repetita iuvant, maybe. This is what is learned. 3 slides on what is learning. Okay, first, there is data. Data are the training and test set we talked about. Okay, we have a finite amount of data where the xi are taken from a certain data distribution on the domain space, and the label are the values of our unknown function. Okay, here is denoted the same notation we use in the other lectures. This is the data. Then there is the model. The model, as I told you, is a subset of all possible functions defined on X. For instance, the model could be polynomials of degree up to k. Yesterday, we have very quickly seen an example where we were considering a model consisting in polynomials of degree up to 5, or another model with polynomials of degree up to 2, and another model with polynomials of degree up to 1. Okay, these are very simple models, and they have very few parameters, or the models we are pervasively talking about are called neural networks. They have so many, much more parameters than polynomials, and this is the model. Okay. And then the error, maybe we call this also loss. Okay, the error is a pointwise measure that allows you to tell how much the estimate you are considering of your function f hat on this point, on that point you are considering, is far from the label you have. So instead of considering simply the quadratic loss, one can talk about, or this is yi. Okay, this can be any measure. We have seen it can be the negative likelihood for probability distribution, can be the L2 distance for regression problems, and I'm not telling you anything about some very important notion, which is regularization, which is something adding to the loss. Okay, the loss is never the single L2 loss that I was showing to you. Anyway, this error metric is usually pointwise, because the error metric you are considering is an average over the whole space. In this case, an average over the whole space X. This is the distribution where you take the X's from. And this is the loss you would like to compute. And this is actually the empirical loss that you are actually able to compute. Okay. And in what we are saying that since we have this finite amount of data, we can only minimize this empirical loss. So we try to solve the problem argmin of r hat of f. We try to find this f hat which minimizes this r hat. And this is more or less the basis of the empirical risk minimization principle that we are implicitly using in whatever we are saying and doing. Okay, this is just something summing up the learning. Okay, but now I should go. Okay, here, let me check if this is to tell you what's the time. No, too late. Okay, so I will skip this. This is a very nice picture regarding the error. I told you that there is this bias variance trade-off, okay, that you can't improve one without decreasing. You cannot decrease one without improving the other one. And this is a pictorial representation of something very similar to this, where the error we are interested is this black line. This error is always the sum upper bounded by the sum of those two errors, and those two errors are more or less the bias related to the bias and the variance we were talking about. Okay. Remember this picture also if you're not explaining it very much, but remember that the error we are trying to minimize is bounded by two quantities, by the sum of two quantities, and usually without additional hypothesis. If we try to decrease one of these quantities, we are going to increase the other one. Okay. And so now, symmetries are important in deep learning. If we know symmetries on a problem, we could try to build a model defined on the orbit space. Okay? So the first thing we should try to solve, the first problem we should try to solve is how to find as many as possible symmetries for a given task. Okay? How can we find as many as possible symmetries of the task? And now this is, I think, very interesting point of view, and it is the basis, the foundation of geometric deep learning. And geometric, it is very, very effective and very clear. But look, this is an image. An image. What is an image? Can you tell me what is an image? Let's try to tell me what is an image. If I ask, you are a mathematician, so if I ask you, give me a definition of an image, grayscale or colored image, as you want, how would you define it? Try.
Matrix. A factor between a domain into a scalar fit, scalar set.
So you say it again. So an image is a
function between a domain to a scalar set.
Okay.
We also got a second answer, which was a matrix.
Oh, I prefer the second one because the first one is the correct one, but you are not supposed to tell me the correct one in the first instance. So let's start from the matrix. Yes, this is correct. An image is a matrix. And in this matrix, you have values, okay? Let's say you have only one value per pixel, so a grayscale image. And yes, I would say this is the most common way of thinking two images for people. But the nice idea here that comes also, actually, it's not.
Sorry, let me ask you.
Yeah.
When you say one value, so the matrix takes values in 0, 1? Is that what you're saying?
No, usually if the image is okay, if the image is black and white, then the matrix has value 0 or 1. That means black, white or black. Okay, but usually an image, to be at least a little bit understandable, should be gray levels, and usually you use numbers from 0 to 255. And those numbers determines the gray level of that pixel. But anyway, just one number per pixel. While in color images, you have 3 numbers per pixel. Is this known? Is this clear, or this is not known?
We can try to guess, but maybe you should explain if it's necessary.
Okay, let me check if somebody's trying to connect. No. No, I was saying, so an image is usually an array, a matrix of numbers, okay? Those numbers can be 0 or 1 for black and white images, or numbers from 0 to 255 for grayscale images, or can be vectors in R3 if we have a color image, because colors are encoded with the intensity of red, green, and blue part. Okay, so in a machine to encode a color, you can't use just one number. You need to use 3 numbers. So usually a color image is not 1 matrix, but would be 3 matrices. Okay, overlapping each one over the other. But assuming this is clear, okay, so it is important that this is clear. So please tell me if this picture of an image is not clear.
It's okay.
Okay, assuming this is clear, now we want to decompose this matrix as a function. What do I mean, decomposing it as a function? Well, you can think of it as another point of view. A matrix can be taught just as a function from this domain, in this case, a grid. Okay, so you can think of it as a portion of Z2 into R. Do you agree that such a function is assigning to every point in a grid a number? So do you agree that this is more or less the same? It is exactly the same as the image before. Of course, a real image would be on a bounded domain here in Z square, and the value that this function can assume are just between 0 and 255, as I told you. Okay, but if I use this point of view, now a color image is very easily described as a function in R3. So this is the first point that I ask you to think, to have clear in your mind. Starting from now on, our data, our training points, which are images, okay? You can think to training points as images for simplicity. These are functions. Those functions are called signals, okay? And in these slides, the signals are denoted by this X, and the domain is called omega. In these slides, the domain will be the grid of certain dimension, okay? Or usually, to make the things more theoretical, you can think of the domain as unbounded. This domain is called geometric domain, the geometric domain for the task. And just to let you understand, there are not only images in the deep learning world. If we are acting, if we are solving a problem on graphs, the geometric domain will be the domain of graphs without labels, without anything, and the function will assign the labels to the nodes and to the edges in the graph. Okay, and this has the in some sense already something to do with the dimension. In this sense, the dimension now is splitted. The high dimensionality of images now is in some sense decomposed as 2 and 3. Of course, the set of functions from year to year is still can be also infinite dimensional. We say we are opening the input data. And in this way, remember why we started all this this slide. We were saying, how can we find as many as possible symmetries? Well, what was the group acting on images for image recognition? Was the translation group, right? Well, the translation group is not actually acting on the image, on the function. It's actually acting on the geometric domain. I can make the translation on the domain omega, and this is the natural space where the translation lives. Okay, the fact that the translations act also on the functions defined on this domain, we will see it comes from the notion called the regular representation on functions on a geometric domain. Okay, but the symmetries lives on this domain, act originally on this domain. Okay. Here a few examples, as I was already told you, showing that this kind of representing the data gives you a lot of additional structure. In particular, for instance, since the space, since this space is a vector space, we call this space C for channels, okay? The C is for channels. So our function will act on the geometric domain and take values in their channels. Channels is always a vector space, R to a certain power. And this means, in particular, looking at data in this way, this means that data points form a vector space. Now, you could say, come on, images are already a vector space. They are matrices. So there isn't any advantage in doing this. Yes, but graphs are not a vector space. While when we look at graphs, labeled graph in this way, the vector space structure of the codomain of these functions translate to a vector space structure of the data points. So this is the set of data points that is the C-valued signals on omega, and this is a vector space. So we are starting giving the data points additional structure. So that now the data is always a vector space in this way. And if we can fix a metric in the channel space in Rn, if we fix a metric in Rn, and if we fix some measure on the geometric domain omega, then we have that the function from omega to this Rn is an Hilbert space. And this means that we can use all the existing theory for these spaces. And in geometric deep learning, you do this a lot. Now, this is beautiful for me that I was born as a differential geometer. In certain situations, can be useful to represent the input data not just as a function, but as a vector field on a differentiable manifold. So not anymore a scalar function, but a vector field. In this case, f of u, that first was living in the channel space Rn, actually lives on the channel space, which is still an Rn, but it is a fiber over the point u of a certain vector bundle over the manifold, the structure from where you are picking up the point u. So mathematically, this channel with this symbol U here is the fiber of a vector bundle of the manifold. And omega, in this sense, becomes just a local trivialization that we use to read the input F. Okay, so this is very interesting, but it's also very, very advanced and complicated, and we will not touch this kind of point of view in these slides, but just to let you know that there is a lot of geometry here. Geometric deep learning is not geometric just because we like to use the word geometry because it is a fancy word. In geometric deep learning, there is a lot of very advanced geometry. Okay. Now, we are talking about symmetries, and we are saying that symmetries are important. I want just to point out something that usually is overlooked, I would say. The kind of symmetries of the task that we are interested on strictly depends on the meaning of the task, on the semantic of the task. For instance, would you say that rotations are symmetries for image recognition? Are rotations symmetries for image recognition? I mean, if I rotate a dog, should it still be classified as a dog also when it is rotated this way, and also if it is completely rotated by 100? Now, I cannot do a dog. Should this still be a dog? I would say yes, right? So do you agree that rotations are symmetries for image recognition, or you have something to say? Exactly. For digits, no. It depends on the task for which image recognition is used. If I'm recognizing dogs and cats, of course, this is these are symmetries, so yes. But if I'm recognizing a 6, this shouldn't be recognized as a 6 when it is rotated by 180 degrees. Yes and no. So it is important to remember that what are the correct symmetries for the task is not usually a trivial task, and they strictly depend on the task, on the semantics on the task, I want to say. Okay, but 4:30. Okay, now knowing symmetries allows you to reduce the course of dimensionality, the effectiveness of the course of dimensionality. And to convince you of this, we can take an extreme case, that is the case where we know all the symmetries of the function we are trying to find, the label function. Well, remember that I told you in the general problem, you need at least epsilon to the power of d training samples. Now I'm telling you that if we were able to know all the symmetries of the label function we're trying to predict, then we would only need one label per class, one training item per class with the correct label. Why? Okay, I realize that it is not clear when I'm waiting for the answer or I'm just pausing to go on. So I'm waiting for an answer here. I'm assuming that the never happening case that I know all the symmetries for my task. And I'm saying that in this case, to learn the correct function on all the possible data I can have, I just need one training example per each class. So let's say I'm classifying cat and dogs. I would just need one picture of a cat with the label cat, of course, and one picture of a dog with the label dog. I'm saying that in this way, with just these two pictures, I'm able to classify every other picture.
And I use the symmetries to enlarge the data set.
If I know the symmetries,
I can enlarge the data set.
okay, you just yes, probably this is what you're saying. You apply every symmetry to the picture of the cat, and whatever picture you obtain, and since you know all the symmetries, you obtain all the pictures. Okay, let's assume the action is transitive, and you obtain all the picture of cats with the correct label cat, and then you do the same on the picture of the dog, and you obtain all the picture of the dog. Okay, so this is of course never happening. Okay, in particular, in any non-trivial problem, we will never be able to find anything close to the full symmetry group. Okay, so we are now studying the symmetries of the task. That is, the symmetries of X that make L invariant. And here is why looking at picture as signals, looking at data as signals, becomes very useful, because there are a bunch of symmetries that we can describe on X coming from symmetries on omega. In this way, this is the formal way to define the regular, what is called in representation theory, the regular representation. If you've done some exam on this topic, you know this, but otherwise it's very simple. If you have a group acting on omega in some way, this means that given omega, an element omega of your set, you can define G dot omega. This is a left group action. And this will be again an element of capital omega. And of course, this we call this group action when this transformation satisfies certain hypotheses. Then, if you do this, you can define given a function f from omega to, let's say, r, then you can define a new function, which is jf, given how? Well, on small omega, this function will be f. You need the inverse here. You can't use the you can't use the direct directly G, otherwise you have a right instead of a left representation, but this is a technicality. Anyway, the important thing is that you can define an action of the group also on the functions defined on that omega. What does it mean? Why we are interested in this? This means that now we can look for symmetries coming in this way. They are not all the symmetries of our function space, but I mean, we said we are not able to find every symmetry in a problem, let's start with simple things. Okay. So let's keep this. Okay. Now, now that we have a way to find symmetry. Oh, by the way, maybe I should tell this. Okay, the action of the group action, the regular representation, the group action on signals is linear. And this means in particular that this is a representation on this space. So we can use representation theory to find this kind of symmetries. Okay. Now I want to focus on two different concepts that, as a mathematician, you probably already know. That is the difference between invariance and equivariance. Sometimes the function we want to predict is not equivariant, not invariant, where equivariance means to be equivariant with respect to a group means that when you compute f of g dot x, invariant would be that f doesn't care the group action, so it remains this way. While equivariance, this is invariance, while equivariance means that when I act on the input by a group element G, what I obtain is similar with respect to the group action to f of x, but it's not exactly the same. By similar, I mean that this is f of x, where I'm acting with the element G. Okay. Now, in this example, we have three different tasks on graphs with n nodes. The first task is graph prediction, the second task is node prediction, and the third task is edge prediction for the same domain omega. And the same action of the group G here is written here. Okay, the group G is the permutation on the nodes. Okay, this n is the number of nodes. That is the vertices of the graph, if you like. Let's focus on the central task, which is the easier to describe equivariance. We are predicting a numeric feature for each node of the set graph. So let's say that let's say the nodes are 1, 2, 3, 4. 1, 2, 3, 4. Now, let's say that for the first node, I predicted this color. For the second node, I predicted this color. For the third, I predicted this color. For the fourth, I predicted this color. Now, imagine I act on the nodes by permuting 1 with 2. So I'm exchanging these two nodes. So I obtain the new 4 nodes, and imagine that your function is invariant. If your function is invariant, your function doesn't care this kind of transformation and will still predict to the new nodes with the new position the same color. So this will be orange again. But this node was the second one. And if the color was correct, it shouldn't be orange, should be light brown or purple, whatever color this is. Okay, so equivariance means that applies in this case means that the new color predicted should be permuted again by the same permutation. So in some sense, there is here a permutation on R4 that is corresponding to exchanging the first node with the second. And the permutation in R4 would be, of course, exchanging the first coordinate with the second coordinate. Okay. Now I just realized that I'm explaining equivariance to a class of mathematicians, so maybe that was useless. Anyway, if some of you didn't know what equivariance was, I hope now he has an idea. Now, in this example, there is a representation in which the first arrow, this arrow, is invariant to rotations. Okay, you see how this is represented. This is an A. The same A is rotated, but since your predictor is invariant to rotation, for him, these 4 points are the same data point. And so he will always predict the same element and the same year, and year. Now, what does it mean? What I want to say? I want to say that this is helping the task because the second arrow, this arrow, which is the classifier, which should give this color to A and this color to B, should distinguish A from B. Well, this classifier is as the life much easier than before, because here there are 16 elements on which it should try the classification. Here there are 4. Okay, so this is easier. So this suggests that maybe when I'm solving such a problem, it may be a good idea to use compositional function in a model where the first piece is invariant. Okay, this example is trying to give you the idea that when I'm trying to classify images, maybe it is a good idea to build a hierarchical model with different parts where the first part is invariant and the second part, or the first 10 parts, are invariant, and the last part is the actual classifier. But in general, in deep learning, this is a very bad idea. Why? This is due on how multi-layer networks work. Since they learn in a hierarchical way, they first learn local details. This is also related to how convolutional neural network works. Remember the lecture of yesterday. So you first learn local details and then function of these details that summarize second level details. Now, imagine a model that learns those local details regardless of their orientation. So this is the original picture, and apply this model to this image. Okay, apply the same model to the image on the left and to the image on the right. In the first layer, this model would recognize 2 eyes, 1 nose, and 1 mouth. Okay, and it would recognize 2 eyes, 1 nose, and 1 mouth in the same positions in the image. So the second layer would say, okay, here I have 1 eye. I have eye here, nose here, mouth here, so definitely a face. okay? But I'm pretty sure nobody would say that this is a phase. What is going wrong in this? Because of the hierarchy in learning and because of the imposed invariance in the first layer. The invariance in the first layer is not compatible with this hierarchical learning because it is losing a vital information, the relative position of local details. The relative position of the eye with respect to the nose, this position with respect to the nose, should be maintained. What's happening here? Here is happening that the eye was rotated in no, they are rotated by the same amount, okay? Okay, sorry, I feel a bit tired and confused. Anyway, this is happening because the first layer is invariant and not equivariant. The first layer should be equivariant. If the first layer is equivariant, then it is preserving, when you are rotating the eye, you are rotating and positioning the information of the eye in the same way. If you rotate the eye this way, then in the new image, this eye should go here. See what I mean? In the new eye, you should rotate the whole image. If you do this, rotating this eye this way, you obtain this and this and this and this, which is still a phase. Okay, so the problem is the invariance in the first layer instead of the equivariance. So, like 35. And so, remember, I called in the beginning, when I told about the Erlangen program, I was talking about the blueprint of the geometry. The blueprint of the geometry is considering every geometry as a group for which we are considering invariant or equivariant properties with respect to. Now, the blueprint for geometric deep learning is something like this: is compositionally building equivariant layers and applying at the end an invariant layer. And this would make the whole function invariant. So yes, this is something that should be clear if you write it. But if you have a function which is the composition of an equivariant function, another equivariant function, another equivariant function, and at the end you put an invariant function, the whole function, the whole composed function, will be invariant. So if we need an invariant function in our model, then we are going to have this invariant function. So you see, we are starting to see the way to build models which are invariant with respect to the action of a certain group. How can we do this? Well, we are just to develop a layer which is equivariant with respect to the action of a certain group G. This action should go through some homomorphism to an action on the channels, on the output space, on the domain, on the codomain of that signal. And then we repeat this construction. The second layer takes as input the channels of before and uses action, the same action, and then we need another homomorphism transforming this action in the new channel space, and so on. So if we can build a single layer which is equivariant with respect to certain actions, to certain groups, then we are almost done, because we can compose all these layers in this way. And this is what we do exactly with convolutional neural networks. Convolutional neural network is composing the convolutional layers, which we have seen are equivariant with respect to translations. Okay, here there are some animation I would like to show to you, but let me check one moment. Okay, I can show you this. Okay, we'll show you one animation on YouTube, and then we can finish the lecture. So if there are questions, just as you know, there are several other slides. I'm skipping a lot. In particular, I'm skipping the fact that we need invariance and equivariance for several other types of transformations, not only translations and rotations, okay? And this requires a multi-scale point of view on the problem, which is very common in science, in data science. And this multi-scale point of view applies techniques from something called multi-resolution analysis. Use in geometric deep learning, you use a lot of wavelets, if you know this concept, this term. And okay, but we have no time, so I want to show you just this nice video. By the way, in the share, you can find the text file where you can recognize this lecture. These are some points that I was using here. Can you still see my... Okay. So I'm showing you a YouTube video, okay? I'm not sure you can hear the audio, but if not, there are the subtitles. Please tell me if you're still viewing the video, because I maximized it.
Yes.
Okay.
Ah, ma forse si vede.
So,
si vedeva molto male. Vediamo solo dei rettangoli ombra che si muovono.
proviamo così, but I think the bandwidth this way.
Okay.
Doesn't work. Funziona,
Poi
Tommaso?
ci fai vedere cose più fighe.
Okay, no, okay, so this is not working. I was just going to show you this animation of this picture that is showing to you that when I rotate the input and I apply a convolutional neural networks, if I visualize by coloring the same shape with different colors corresponding to different numbers, when this thing is moving, then also this picture is moving, showing that it is convolutional neural networks are not invariant to rotations. Okay, this is what the video is trying to convince you, that convolutional neural networks are invariant to translations, but not to rotations. And if you do the same with the newly developed model, one of the first developed in this topic of geometric deep learning, which are called geometric convolutional neural networks, then you will find that they are invariant also to equivariant, sorry, also to rotations. And you will see that when you rotate this image, this is what the video was showing, this other image will remain fixed. Sorry, this other image will rotate the same as this, but with the same colors. You see what I mean? While when this is rotating, then the colors change. Okay. I think we can stop here. Yes, we're right in time. And maybe if there are questions, I guess this was a peculiar lecture. I can stop the screen sharing.
Me vedi?
Sì.
Okay, any questions? No, I mean, I still have a question. It's the same question I asked at the beginning of the lecture, and maybe I'll try again. But I mean, this is one of those moments in which I would like to take you, Maurizio, to the corner and have an independent conversation. Everybody else can stay or leave as they wish. My question is, could you walk us through sort of the how you would set up image recognition problem in terms of your original formulation, in which you have some variables x, function f, some values y. In that particular case, who are these x, f, and y? I mean, today you told us something about how to codify image, but now I'm still left. I can't quite use that to figure out who your f's, x, y's are in this case.
I'm not sure I understand well the question. You are asking what are x and y for images and f for images.
Well, let's choose a problem. For example, the fake person, building a nice fake person, a good-looking fake person.
Okay, this is not a recognizing image problem.
Okay, all right, you're right. But let's choose it anyways. Okay. I want to train a computer to make fake photographs.
Okay, for this you use a completely different family of models that are called the generative models. And they are nowadays the most used family models in this sense are called diffusion models, which works in a very nice way that I can tell you. I'm not sure there is nothing in geometric deep learning related to these diffusion models. And of course, it is a very interesting geometric deep learning question, whether geometric deep learning can be applied in some sense to this kind of models.
But sorry, you say one needs different models. Does it still fit in to the very general setup that you showed us the first in terms of finding the best function to fit certain x and y's?
What are the y's? Let me ask you.
That's my point. What are the y's? What are the x's?
Okay, okay, so I get your point now. So what I described to you is something in machine learning called supervised learning. Supervised learning means that you have the X's and the Y's. Okay, there are some problems, very important problems, where you don't have at all the Y's. For instance, when you have to do clustering, you have just a bunch of points and you're asking yourself whether those points could be divided in a partition with different meanings. You have a bunch of pictures and you would like to distinguish in those pictures the cancers and not cancers, but you don't have labels for these pictures. Surprisingly, there are techniques called clustering techniques doing this kind of job. And then you have something very interesting, which is what you do with these diffusion models, and I'm telling you now. A very nice problem where you can use the X in some sense as the Y. And I can, if you give me 5 minutes, I can describe to you this kind of structure. Can you see again my screen, right? Okay. So imagine you don't want to recognize images, but you want a model which is able to generate images. Okay, so I'm describing to you the most elementary way to do this. That is not the way that is used in the website I was showing to you, but this is very easy to explain. So let's build a usual neural networks. This is the image. Let's say a 3x3 image. So 9 point, okay? And let's say now that this image is sent to 5, let's say 7 neurons, then to 5 neurons, then to 3 neurons. And now I repeat the same structure, sort of an imbuto. I don't know the English word for it. Okay. And you have only the images, okay? You don't have labels, because your problem is not recognizing the image, but your problem is building a model that can create new images. Is the problem clear? Now, you can train this model with labels. In which way? What is the label of this image? I mean, to train a model for what I have told to you, you need X, and then you need a Y here. And your model should minimize the f hat of X minus Y, sum over all X's. Okay? Clear. So I need the Y here. I have X, the model is giving me f hat. I need the Y. What is the Y for this X? What is this task? This task is building images. So the output of this task should be an image. So the only label you can use is Y equal to X. So what happens now? Assume you have built a model, you have trained such a model, and now your model is very good in giving you a certain image X, is very good in outputting, giving you as the output of this model, the trained model, the same picture. Not really the same, because of this lowering dimension, you're losing information, but you train your model, and let's say the model is working. Okay? Now the magic happens. Throw away this part. Okay? The model is trained. So if you give him an image from here, it will give you something resembling this image. Now, assume that you now want to generate an image close to this picture of a dog. And assume that if you put in the first part of the model this picture of the dog, you here obtain 3, 42, and -10. Now, just put here, instead of -10, -9.9, and you agree that you will obtain another picture, right? That, if everything is working well, should be very similar to the original picture because of continuity and so on. So you obtained in this way a predictor, an f hat, that can take as input elements, vectors in R3, and gives you as output an image. And this image, if the model is working, should be a real looking image.
Sorry, so what you're saying is the function, the function in the best function, the function in your neural network, is supposed to take an image of the dog, throw away 99% of the image, manage to figure out which are the very few defining characteristics of the image of a dog, and then reconstruct the dog as much as possible. And if this is a good function, then it means it has managed to do this efficiently, very well.
Yes, I wouldn't say efficiently, but very well. Efficiently means very fast and so on.
Yeah, okay.
All of
Well,
these
okay, but it's simplified. It simplified the dog to very few.
yes.
With a number of data that you wanted to reduce it to, and can still get a dog back.
Yes, this is called latent space, where you are summarizing the information. This is actually something that we already do in another topic. If you never use PCA, principal component analysis, you're doing something very similar. I don't know if you ever use that. It's a standard tool in statistics. Is a way to find the principal component. You have data in a very high dimensional space, and you decompose this space where the variations of data, the correlations of data are higher, and then you throw away the dimension, the coordinates that are carrying less information. So you originally had 1000 axis. You were working in R to the power of 1000, and you choose the first 10 principal directions, which are the direction chosen in a way that carries the most important information, and you can throw away the other 990 directions, and your data is still meaningful. And so we are doing something the same here. We are throwing away 6 dimensions because the original data was of dimension 9, and we are training the predictor to condense in 3 principal components the most possible information from that data.
I see. Okay, so you're saying this does fit into the framework that you had originally described. X,
In this
Y,
way.
and fx.
This is called the semi-supervised or self-supervised learning. I think it's self-explanatory, the term.
Yes, and so I mean, what you're saying is, so same framework, but instead of using the neural networks that you were talking about before as being the class of functions, you would now introduce a different class of functions, which are somehow these self-supervised learning objects, and try to work with, and then try to find the best F star in that class.
Yes.
Is that correct?
Yes.
I see.
Perfect.
Uh-huh. Cool. Grazie Maurizio.
Grazie a voi.